We saw how the canonical ensemble allows us to consider a grouping of states with different energies and put them together into a partition function that allows us to do statistical mechanics. We saw that this could be much easier than being forced to consider only the states of a specific energy like we did in the micro-canonical ensemble. But in some problems, especially quantum problems, it becomes too restrictive even to consider states of a definite particle number. We can create a new kind of ensemble where we allow microstates of different energy and different particle number all to be counted at the same time. This ensemble is called the Grand Canonical Ensemble. We can derive the distribution of the Grand Canonical Ensemble by considering a system, again immersed in a reservoir. The reservoir is held at a constant temperature so that energy can flow in and out of the small system. But the temperature only controls the flow of energy. To allow the reservoir and system to exchange particles with each other, we specify that the reservoir also has a specific chemical potential. This means that the chemical potential and temperature of the system are known, but it could have various energy or number of particles within it. One way to imagine this is to draw an imaginary region inside of a gas and just watching particles flow in or out of that region. The number in the region at any time is not definite, but it does give it a definite energy when there's a certain number of particles in there. Again, we want to calculate the probability of observing the system in a certain amount of energy with a certain number of particles. To do this, we'll use the fact that energy is conserved, and we'll use the fact that the total number of particles is conserved as well between the reservoir and system. The system is, again, in an exact microstate, so its multiplicity is 1, whereas the multiplicity of the reservoir depends in some possibly complicated way on the amount of energy in the reservoir and now on the number of particles in the reservoir. Since the total multiplicity is the product of both pieces, it is essentially equal to the multiplicity of the reservoir. Again, we want to approximate the multiplicity function since it's related to probability. To do this, we'll first take the logarithm and expand it in a Taylor series with a small deviation for UR, because UR is equal to the total energy U minus the energy of the system, and this time a small deviation NS from the total number of particles in the system, since NR is equal to N minus NS. Our Taylor expansion will then look like this. We have one term for the derivative with respect to the energy, and we get another term, a new term, for the derivative with respect to the number of particles, N. These derivatives, as the same way they did in the canonical ensemble, will be related to various thermodynamic properties. The logarithm of omega r is equal to the entropy of the reservoir divided by Boltzmann's constant K. So when we do this derivative, we can think of this as ds du, which is equal to 1 over the temperature. So our probability log omega to observe a given microstate is going to be related to the multiplicity of the reservoir minus the energy of the system over kT minus a second term. Now we have the derivative of, log of omega with respect to n. That would give us ds dn, which is related to the chemical potential. It comes out to I'll remind us, ds dn is equal to negative mu over t. So this derivative has a minus in the derivative and a minus from ns. So we get plus mu ns over kBt. This implies that the multiplicity function is equal to some constant times the exponential of minus es of the system over kT plus the chemical potential of the reservoir times the number of particles in the system, ns, over kBt. Since multiplicities are directly proportional to probabilities, we've got our final desired result. The probability of observing a microstate in the system, J, is equal to some constant of proportionality times the exponential of minus the energy of that J microstate minus mu times the number of particles in that J microstate divided by Boltzmann's constant times temperature. This distribution here is called the Gibbs distribution. But that's just a name for it. It's not necessarily related to the Gibbs free energy. It's actually related to a different free energy that we haven't talked about yet, but we know how to handle it, as we'll see. The normalization factor here, capital Z, with serifs on the top and bottom, is called the Grand Canonical partition function. It is the sum of all of these Gibbs factors over all possible microstates of any energy and any number of particles in the small system. Grand partition function. And this acts just like the partition function did for the canonical ensemble. Let's work out some of those statistical results the same way as we did for the canonical ensemble. Again, the average energy to be found in the system is the expectation value of E for all of the states that have probability. We'll skip the derivation this time because it's very similar, but this can also be written as the negative derivative of the grand partition function with respect to the beta parameter, which is still defined as 1 over kBt. Remember, we can also write this as the derivative of the natural log of that partition function with respect to beta. In the grand canonical ensemble, we also have the ability to discuss the average number of particles in the small system. It will be the expectation value of n in the jth microstate times that probability t of the jth microstate. If we work out this quantity, we find that it can also be expressed in terms of a derivative of the partition function. And this will be very suggestive. We find that it's equal to 1 over beta times the partition function times the derivative of the partition function with respect to the chemical potential. We can see how this works. If we take the derivative of this expression with respect to the chemical potential, it will bring down a factor of n over kT. The beta is there to cancel the kT, and the nj from the derivative chain rule becomes the nj in the expectation value formula. We can also write this derivative as kT times the derivative of the natural log of the grand partition function with respect to the chemical potential. The way we think of the chemical potential here is a little bit different than we've seen in chapters 5 and earlier. The chemical potential is now viewed as a parameter which controls how many particles might want to flow into or flow out of this small system. If mu is large, then it will force more particles into the system. And if mu is small, particles will prefer to leave the system. So mu is a parameter which governs the average number of particles within the system. Just like beta is a parameter that governs the average energy within the system. In exact analogy to the canonical ensemble, we can also define the entropy for the Grand Canonical Ensemble. To do this, we'll use a starting point that we derived earlier. The entropy can be expressed in terms of probabilities as minus Boltzmann's constant times the expectation value of the logarithm of the probability. Since our probabilities are equal to 1 over the grand partition function times a Gibbs factor minus beta E minus mu n. This entropy, if you work out, can be shown to be equal to Boltzmann's constant times beta times the average energy minus Boltzmann's constant times beta times mu times the average particle number plus Boltzmann's constant times temperature. Boltzmann's constant, not times temperature, just Boltzmann's constant times the logarithm of the grand partition function. Again, we can turn this around to get an expression that will lead us towards thermodynamics. Multiplying both sides by t, I get Ts. These two cancel. This one cancels just to mu, and a kBt shows up here. This means that the quantity minus kBt times the logarithm of the grand partition function is equal to the average energy minus the temperature times the entropy of the system minus the chemical potential times the expected number of particles in the system. And here again, we won't belabor the point, but we can easily make the leap to interpret the system and all its microstates as the entire macroscopic object. And therefore, this average expected energy for the small system can be interpreted as the internal energy of the entire system. And the average expected number of particles can be interpreted as the entire number of particles in the system. And what we see here on the right is equivalent to a type of Legendre transform. We haven't seen this one in particular. Remember what a Legendre transform does. It takes one potential, subtracts the product of a conjugate variable product, and uses that to change the independent variables. If we changed from U, internal energy, to U minus Ts, or Helmholtz energy, we made a change from entropy as a natural variable to temperature as a natural variable. So this subtraction of mu n does the same thing, changing into a new thermodynamic potential that has the chemical potential as a natural variable and the particle number as a derivative. We call that new thermodynamic potential the grand potential. It's actually sort of humorous how we just put grand in front of everything, and mostly it looks the same. The grand potential has a symbol of capital Greek letter phi, and it is equal to minus Boltzmann's constant times temperature times the natural log of the grand partition function. The natural variables of the grand potential are temperature volume, and chemical potential. Therefore, we can see that the derivatives of the grand potential give us the entropy, the pressure, and the number of particles, all with a minus sign in front of them. By looking at the Euler integral forms, we can also conclude that the grand potential is actually just equal to the opposite of pressure times the volume for that system. If we want to change to a more familiar thermodynamic potential, such as the Helmholtz free energy, we can simply undo the Legendre transform by taking the grand potential and adding chemical potential times particle number. From these relationships here, all thermodynamics and all response functions and state variables follow immediately. So our summary of the Grand Canonical Ensemble is to look at a system, enumerate or specify all possible microstates J with energies Ej and particle numbers Nj in the system. Calculate the grand partition function by summing the exponential of minus Ej minus mu n j over kBt. This part is usually the most difficult and requires to know some pattern of energies or pattern of particle numbers to get the sum completed. Once the sum is done, we can calculate the grand potential by taking the natural log of the grand partition function. And then we can calculate all of thermodynamics by doing the various derivatives or Legendre transformations on the grand potential.